This video is going to be looking at how to find limits of recurrence relations, both in situations where we're given the recurrence relation itself, and also in situations where we've actually already found the ordinal rule or the particular solution for a sequence, and we want to think about a long-term behavior. So starting with if we're given a recurrence relation, going to look at something that doesn't look that nice at first. So I'm going to tell you that x n plus 1 is equal to xn squared plus 15 all over 8. Sorry about that writing, my pen's just playing up a little bit there. So we've got this, and you'll note that I haven't yet told you the first term, which we're going to need to know. Now, the reason I haven't told you that is because the limit may vary depending on what first term we use. So I'm going to start with one that works fairly nicely for us. If we take a first term of 2, then you put it in here, so xn plus 1, we're doing the previous term squared, plus 15 over 8. Speeding yourself up here, if you have a calculator handy, then what I'd recommend is you press 2 equals, and then you type n squared plus 15 all divided by 8, and then you'll just be able to keep pressing equals. If you do that, you'll get the next few terms fairly quickly. And at first, the pattern doesn't look that clear. So 2's our first term, and then our next term here is 2.375. Our next term is 2.580. I'm rounding by this point. Then we're getting 2.707 to 3 decimal places. We get 2.791. If you keep going, you'll find it doesn't grow and grow and grow. Well, each term is bigger than the previous one, but it doesn't diverge to infinity, is what I mean. You should find that it's converging to a limit of 3. So in this case, if we take the starting value of 2, we get a limit of 3. Well, what happens if we use a different starting value? If you do x1 equals 4, if you can pause the video and give it a go, I'd recommend it. But if you go through, I'm not going to write down all the situations in this case. You should find again, you get a limit of 3. This time it goes down towards the limit, but once again it converges to a limit of 3. So maybe it converges to the limit of 3 wherever we start. We've started below 3. We've started above 3. If we do x1 equals 6, you should find by the time you do your first calculation, it gets bigger. So it doesn't seem to be going towards 3. And if you keep going, it just gets bigger and bigger and bigger. It diverges. It doesn't tend to any limit, or any finite limit at least, in this case. So certainly it doesn't always go towards 3. Now, we could just continue to try different starting values, but how do we know how many possibilities we need to try to get a sense of it? Well, it's really useful to think about, to be able to investigate whether 3 is the only possible limit or whether there are other possible limits out there. So what we can do for that is to say, well, if some value k is a limit, so we're going to say if k is a limit, then if we put k in, we must get k back out as an output. So what I'm saying there is if xn is equal to k, then we're going to get our input is equal to our output, because we can't reach our limit and then go back off it. And this is a fancy way of saying if xn equals k, we're going to get xn is equal to xn plus 1 is equal to k in any case where k is a limit. So let's put that into our equation. Let's replace all our xn's and all our xn plus 1s with k and see where we go. Well, we're going to end up with k equals k squared plus 15 all over 8. Okay, it's not the nicest, but it's just a quadratic equation. So now we can just rearrange this. I'm going to skip a couple of steps in rearrangement here. We're going to get k squared subtract 8k plus 15 equals 0. And if we factorize, we'll get one thing we shouldn't be surprised by, of k equals 3. That, hopefully, we're expecting. We knew 3 was a limit. But we end up with another possibility of k equals 5. Now, this is a weird one, but if we look back at our sequence, If you substitute 5 into here, you do 5 squared, 25, plus 15 is 40, divided by 8 is 5. So if you start with 5, it stays there. So 5 is a limit, but it's only a limit if we start at 5. So we call it a fixed point, and there would be a limit if x1 equals 5, but that turns out it's the only situation where we get that limit, whereas there's lots of situations where we get 3. There is language to describe these which you don't really need to worry about. 3, we'd say, is a stable fixed point because points around that go towards 3 and still have a limit of 3. 5 is an unstable fixed point. If you try starting at 5.01, you'll find it diverges. If you try starting at 4.99, you'll find it goes towards a limit of 3. So 5 can be a limit, but it's only one special case of our starting values where we get that. So that's the first thing you need to be aware of when you're trying to find limits there, is that we're taking our recurrence relation and we're replacing both xn's and xn plus 1s with k, and what the values of k there are our possible limits. And that's always a way of finding possible limits. Now, you might be given questions where you're given the ordinal rule already. You're already given a particular solution for whatever recurrence relation, or you might have found it yourselves in a more complicated recurrence relation, and you'll be asked to describe the long-term behavior. So, starting fairly nice and easy, let's imagine we've got the nth term is 2 over n squared. Well, in this case, as n gets bigger and bigger, 2 over n squared is going to get smaller and smaller and smaller, closer and closer to 0. So this would have a limit of 0. We can write this, if we want, as xn tends to 0 as n tends to infinity. Or we can write the limit as n tends to infinity of xn is equal to 0. These are all valid notations for saying that. We can just say the limit is 0 or it converges to 0. So that's a nice, easy situation to look at. But are they all that easy? No, these aren't the hardest questions, but there are a few different situations you need to be ready to be aware for. So, next one, just taking up one notch. What if I tell you xn is equal to 5 subtract 7 over n? If you're in any doubt, grab a calculator, put in the big value of n. But if you put in n is a million here, you're going to do 5 subtract 7 over a million. You're going to get an answer really close to 5. When n's a billion, you're going to get an answer even closer to 5. So we must have that the limit of xn as n tends to infinity, in this case, is just going to be equal. Sorry, my pen's playing up here. It's just going to be equal to 5. So this form was fairly nice and easy to see that, and this is probably not a surprise without even putting stuff into the calculator. What if we go for a slightly weirder fraction? Let's imagine we have xn is 3n squared plus 2 all over n. There's a couple of ways we can approach this. One thing you could do is notice that you've got this quadratic term on your numerator and you've got this linear term on your denominator. Now, as n gets big, the quadratic term is going to get bigger way faster than the linear term. So we should expect that the numerator will get bigger a lot faster than the denominator, and therefore it will diverge. A way of showing this even more clearly, and if you're asked to determine this in an exam, it might be useful to find a way to show it. If you split this fraction up as 3n squared over n plus 2 over n, well, we can simplify that first one. We're going to get 3n plus 2 over n. And because 3n diverges, 3n plus 2 over n is going to diverge. That 2 over n is converging to 0, but that 3n is exploding there, so that diverges. Exploding isn't a technical word there, that's just me emphasizing the behavior. Okay, next one to look at, a couple more, just getting gradually more complicated here. What if we've got xn is equal to 4n squared plus 5n all over 3n squared? Well, in this case, we've got a quadratic term on the numerator and a quadratic term on the denominator, so they're going to grow roughly as quickly as each other. Well, in order to see what's going on, if we split this fraction up, so if we have 4n squared over 3n squared plus 5n over 3n squared, well, now we can simplify, and we're just going to get 4 over 3 plus 5 over 3n. Well, We know that 5 over 3n will tend to 0 as n tends to infinity. That's very much like the first couple we looked at. So the whole xn is just going to tend to that 4/3 as n tends to infinity because our last bit's going to become insignificant. It's going to get closer and closer to 0. Again, you can always check here by whacking a large number of n into your calculator. Really good way just to make sure you haven't made a mistake somewhere along the way. We'll look at one more that requires a bit more creative algebra now. Maybe not to spot, but certainly to justify. So let's say we've got xn is 6n plus 5 over n plus 3. In this case, we have a linear term on the numerator, linear term on the denominator. So again, they're going to go roughly as quickly. We're not expecting to go to 0. We're not expecting to go to infinity. If you want to be able to spot it, just going back to the previous one a moment, if we look here, when we said we've got the quadratic terms on top and bottom, the linear term was never going to really matter. That was going to be insignificant. So it was going to be approximately 4n squared over 3n squared. When n is big, that 5n becomes irrelevant compared to the 4n squared. So just looking at those quadratic terms was what gave us our 4 over 3. So in this case, if we just wanted to predict, we could say we've got a 6n on the top and then on the bottom. When n's big, that 5 and that 3 will make very little difference, and we'll probably just be left with 6n over n, and then we can simplify. If we want to justify this, we want to do a clever factorization here. We want to be able to factorize out n plus 3 on the numerator. In order to do that, well, we know, so I'm going to put a 6 there because I know I want to get 6n when I expand. But if I do that, I get 6n, which I want. We get plus 18, which we don't want. We want plus 5. So we then need to subtract 13 to get the answer we want there. Now we can split our fraction, and now we can write as 6n plus 3 over n plus 3. Well, we can see that that's going to go nice, and then subtract 13 over n plus 3, and now we can go through and simplify what we've got there. So we're just going to get 6, subtract 13 over n plus 3, and now we can happily state that the limit as n tends to infinity of xn is just going to be equal to 6. And from there, actually, we can see it's going to be equal to 6, but it's going to approach 6 from below, as in it's going to go like 5.999 rather than 6.001 because we're subtracting a number from it. But that's the sort of algebra you want to give if you're being asked to justify how you can see that's the limit, rather than just working it into your calculator. Thank you very much.